you feel like you're sitting perfectly still right now,
Right.
but you, the chair you're sitting in, and our entire Milky Way galaxy are actually hurtling sideways through space at a staggering 1.4 million miles per hour.
Yeah, 1.4 million. It really is a jarring disconnect, isn't it?
I mean, it's wild. 1.4 million miles per hour. There's no engine, no feeling of acceleration, just this relentless, completely silent drag across the cosmos.
Right, because we instinctively trust our inner ear, and our physical senses to tell us when we're in motion. But when the vehicle you're riding inside is an entire galaxy, those local biological sensors are just entirely useless. The reality of our local cosmic neighborhood is profoundly different from what we experience on a random Tuesday afternoon.
Yeah, that sheer speed brings up an immediate and honestly a somewhat unsettling question for me. Where exactly are we going so incredibly fast? And more importantly, what in the universe possesses the sheer mechanical power to pull a whole galaxy at that velocity?
It's a heavy question, literally.
Definitely. So today we're taking a deep dive into a really fascinating set of astronomical sources that explore this phenomenon known to science as the Great Attractor. The mission of today's deep dive is to figure out exactly what this invisible force is, how scientists even manage to measure our movement toward it, and ultimately what it means for our fleeting place in the grand architecture of the universe. So, okay, let's unpack this.
Well, to start, we really have to isolate what kind of motion we're actually talking about here, because, galaxies are always moving. But the sources we're analyzing today reveal that this particular motion isn't just your standard drifting.
Right, it's something else entirely.
Exactly. We're looking at a massive, invisible gravitational anomaly. It is dragging our entire region of space toward a specific deep space destination. So it's a targeted pull, completely distinct from the general, overall behavior of the cosmos.
And to really get the mechanics of this, I think we need to look at the historical context from the sources, specifically around the 1970s. Right? Because up until that point, the standard cosmological model was really built around the uniform expansion of the universe. The whole idea was that space itself is stretching.
Yeah, think of a three-dimensional digital grid, like a wireframe model in a computer program where every intersection on that grid is a galaxy.
Okay, I'm picturing it.
So if you click scale up on the entire model, the grid lines stretch. Every intersection moves away from every other intersection uniformly. In astrophysics, this baseline stretching is known as the Hubble flow.
The Hubble flow. Right?
Yeah, and the assumption back then was that our Milky Way was just another intersection on the grid, passively moving apart from everything else as the universe expanded.
But then astronomers start really analyzing our specific motion in the 1970s, and they realize, wait a second, we aren't just passively riding the grid. We have what they call a peculiar velocity.
A very peculiar one, yeah.
Right. We are shearing across the grid lines, completely off that standard expansion course, and we're being pulled by an incomprehensible force hundreds of millions of light years away.
Yeah.
I always think of it like being on a raft on a really wide river.
A raft, okay.
Yeah, so the river's getting wider, so all the rafts are naturally drifting apart from one another. But suddenly you look down and realize your specific raft is caught in this massive, unseen undercurrent, and it's dragging you violently sideways toward a drop-off.
I like that. The raft analogy works really well for the pulling sensation. But remember, space isn't a two-dimensional river. We have to adjust the geometry a bit.
Oh, right, because it's happening in every direction at once.
Exactly. It's volumetric. We aren't just being pulled downstream. Our entire local cluster of galaxies is being drawn toward a massive gravitational basin from all three dimensions simultaneously, even while the space between everything continues to stretch. What's fascinating here is how that tension between the universe's outward expansion and this localized gravitational pull really forced scientists to rethink the layout of our cosmic neighborhood.
Which brings up a mechanical question that the sources address, and it blew my mind. How did they actually measure that? I mean, if everything in the universe is moving and stretching all the time, what fixed point could astronomers in the 1970s possibly use as a cosmic speedometer to realize we were moving sideways?
Well, the brilliant part is they didn't use a fixed point. They used the afterglow of the Big Bang itself.
Wow, okay.
Yeah, it's called the cosmic microwave background, or the CMB. When the universe first cooled enough to become transparent, it released this huge flash of radiation that still permeates all of space today. In theory, that radiation should be a perfectly uniform temperature no matter which direction you look in the sky.
But it wasn't uniform when they measured it, right? Because of how we were moving through it.
Exactly the opposite of uniform, actually. Astronomers noticed the CMB was slightly warmer in one specific direction of the sky and slightly cooler in the exact opposite direction, which is just a classic Doppler shift.
Oh, like how an ambulance siren sounds higher pitched as it drives toward you because the sound waves are being compressed in front of it.
Yeah, and then lower pitched as it drives away and the waves stretch out.
Right.
Yes, exactly like that, but applied to the ancient light of the universe. Because we are hurtling through space at 1.4 million miles per hour, we are literally plowing into the cosmic microwave background in front of us.
That is just so wild to picture. We're physically ramming into the afterglow of the Big Bang.
Right. And that forward momentum compresses the microwave radiation, shifting its frequency up, which makes it appear infinitesimally warmer. Meanwhile, the radiation behind us is being stretched out, making it appear cooler. That temperature differential, the CMB dipole they call it, was the smoking gun. It proved mathematically that we were being dragged off course.
Okay, but if the math proves you're being dragged by a massive undercurrent, the obvious next step is to just look in the direction you're being pulled and see what is dragging you. We knew the heading, we knew the speed, so why didn't the astronomers in the 70s just point a telescope in that direction and take a picture of this great attractor?
You would think it'd be that simple, but they ran into a localized geometry problem. They tried to look, but they hit a physical barrier that blocked optical telescopes entirely.
And the sources refer to this barrier as the Zone of Avoidance, which is just an incredibly dramatic name for what is essentially a brick wall in space.
It really is a brick wall.
Yeah, so the Great Attractor happens to be located directly behind the thickest, most opaque part of our own Milky Way. If you picture the Milky Way as a flat, spinning disk like a vinyl record, we are sitting somewhere in the middle of that record, and the gravitational pull is coming from directly outward along the flat plane of the disk.
It is an incredibly frustrating vantage point for an astronomer. To see the Great Attractor, we have to look straight through the densest cross-section of our own galactic home. We're talking about looking through 100,000 light years of thick, star-forming molecular clouds, interstellar dust, and just billions of intervening stars.
But wait, we have space telescopes. I'm sure listeners are wondering this too. If this dust is in the way, why can't we just point a telescope slightly up or wait until the Earth orbits to a different position? I mean, if we can see galaxies billions of light years away, why can't we just peek around our own local dust?
Because we are completely embedded inside the dust pane. It's not just a localized cloud in our solar system that we can orbit around in a few months. The dust is the structural material of the galaxy itself.
Oh, so we're trapped in it.
Completely. No matter where the Earth is in its orbit around the Sun, we are still trapped deep inside that 100,000 light-year wide disk. Optical light, the kind of light the human eyes process, and the kind that standard telescopes capture, simply cannot penetrate it. The dust grains absorb and scatter the light completely.
I mean, isn't it slightly maddening that our own home galaxy is exactly what's blinding us? It's like trying to navigate a high-speed car down the highway, but your own windshield is just plastered in thick mud. You know you're moving fast, you can literally feel the engine pulling you forward, but you can't see the road ahead because your own vehicle is physically blocking the view.
That's a great way to put it. It highlights how observational astronomy is fundamentally limited by our physical location.
Yeah, the irony of human astronomical supremacy is glaring here.
Well, yeah, we tend to view the universe from this assumed omniscient top-down perspective, like we can see everything. But we aren't outside the box looking in. We are trapped inside a dusty, crowded galactic disk trying to peer out through all this static.
But scientists don't just accept a muddy windfield. If they can't look through it with normal light, the sources detail how they essentially learned to change the size of the light they were looking for. This was the technological leap that finally allowed us to pierce the zone of avoidance, right? Advanced infrared and radio astronomy.
Right, they had to bypass optical light entirely. And to understand why this works, think of the dust in the Milky Way as a field of tiny pebbles scattered in the shallow water at a beach.
Okay, pebbles on a beach.
If you create a tiny, high-frequency ripple in the water, it hits a pebble and scatters in every direction. That's optical light hitting cosmic dust.
It just bounces off and creates a mess of scattered light so we can't see what's behind it.
Exactly. But if you have a massive, deep ocean swell rolling in, it just washes right over those pebbles as if they aren't even there. The physical wavelength of the swell is too large to be disrupted by something as small as a pebble.
Oh, that makes so much sense.
Yeah, and infrared light has massive wavelengths compared to optical light. It simply rolls right over the cosmic dust grains uninterrupted. Radio waves are even longer, sometimes meters long, and they pass almost entirely unimpeded through the thickest parts of the Milky Way.
So instead of trying to look for visible light, they tuned radio telescopes to pick up the specific frequencies emitted by hydrogen gas in distant galaxies, which cut right through the zone of avoidance like a knife. And what they found waiting on the other side of that dust curtain wasn't just a standard cluster of galaxies, and it wasn't just a giant black hole.
No, it was much bigger than that.
The Great Attractor was revealed to be the gravitational core of a hypermassive supercluster.
Yeah, when the radio and infrared data finally compiled a map of that region, the scale of what they saw fundamentally altered our understanding of universal architecture. When we say a supercluster in this context, we really have to strip away our everyday understanding of mass.
Here's where it gets really interesting, because the numbers provided in the text are just tough to even conceptualize. This isn't just a handful of galaxies. The Great Attractor contains tens of thousands of galaxies, all packed incredibly tightly together around a central gravitational point. The estimated mass is tens of quadrillions of times the mass of our own sun.
And we have to remember that our sun accounts for over 99% of all the mass in our entire solar system.
Which is insane to think about.
Right, so now pack tens of quadrillions of those into a concentrated cosmic core. If we connect this to the bigger picture, this immense concentration of matter dictates the curvature of spacetime for hundreds of millions of light years around it. It creates a gravitational well so steep that our entire local universe, including the Milky Way and our neighboring Andromeda galaxy, is essentially sliding down the slope toward it.
Wait, let me challenge that mass calculation for a second based on the sources. If there is that much mass, tens of quadrillions of suns sitting right next door in cosmic terms, why isn't the sky incredibly bright in that direction? Even if the dust blocks visible light, shouldn't our infrared and radio telescopes be utterly blinded by the glow of that many stars?
That is the exact discrepancy that forced astronomers to look beyond visible matter.
Oh, right.
Yeah, when they mapped the Great Attractor in infrared and radio, they certainly found a massive glowing concentration of galaxies. The Norma cluster, for instance, is absolutely massive, but when they calculated the light emitting from all those stars, the mass of the visible matter didn't even come close to accounting for the gravitational pull required to drag us at 1.4 million miles per hour.
So it just wasn't heavy enough to be the anchor.
Nowhere near heavy enough. To balance the gravitational equation to generate that much pull, astronomers had to infer the presence of an ocean of dark matter.
Dark matter.
Exactly. Dark matter doesn't emit light, it doesn't emit radio waves, it doesn't interact with electromagnetism at all. It only interacts with gravity. So the Great Attractor isn't just a dense pile of glowing stars, it is a colossal, invisible scaffolding of dark matter that has trapped tens of thousands of galaxies within its gravitational web.
So we are being dragged by a dark matter behemoth that we can only measure by the way it warps the motion of the galaxies trapped inside it. That is staggering. I mean, you think about our Milky Way with its billions of stars, and it feels unimaginably huge. But in this framework, we are just a tiny speck getting vacuumed up by a dark matter anomaly.
It definitely puts things in perspective.
But the source material takes us one step further, which is crazy. Just when astronomers mapped the Great Attractor and thought they had found the ultimate anchor of our local universe, new data arrived.
Because observational astronomy is constantly refining itself. And as our radio surveys reached even deeper into the cosmos, peering further beyond the Great Attractor, the map had to be redrawn again.
Right. It turns out the Great Attractor is not the final destination. Recent data shows that the Great Attractor, with all its tens of quadrillions of suns and its massive dark matter scaffolding, is itself moving.
Yes, it is.
It is being pulled, along with us and our entire supercluster, toward a much more distant, unimaginably larger megastructure called the Shapley Supercluster.
This raises an important question about the limits of cosmic structures. For decades, we operated under the assumption that the Great Attractor was the prime mover in our corner of the universe. To discover that it is just a subordinate mass being dragged by an even greater gravitational force, well, it challenges our understanding of the cosmic web. Where does the hierarchical chaining of mass actually end?
It's the ultimate set of Russian nesting dolls. We're just this tiny doll sitting inside the Milky Way doll. The Milky Way doll is being yanked toward the Great Attractor doll. And now we realize the Great Attractor doll is just being swallowed whole by the Shapley Supercluster doll. We aren't even the main event. We're just a middleman in a much larger gravitational chain.
The nesting doll concept is a really helpful way to visualize the hierarchy, though the reality looks a bit more like water flowing along a vast three-dimensional spider web.
Oh, a spider web, okay.
Yeah, the universe is structured in filaments of dark matter and gas. Galaxies flow along these filaments, accumulating in the nodes where the filaments intersect. The Great Attractor is a massive node, but the Shapley Supercluster is an even more massive node, pulling entire filaments toward itself.
Wow.
It is relentless, cascading flow of mass across the universe. Smaller structures inevitably fall into larger structures, which in turn flow toward the densest concentrations of matter that exist.
It is wild to consider that this violent, high-speed cosmic assembly is happening right now, in total silence, while we go about our daily routines. I mean, we've covered a tremendous amount of ground in the sources today. We started with the sheer physical speed of our galaxy. We walked through how astronomers used the ancient radiation of the Big Bang as a speedometer to prove we were moving. We hit the brick wall of the Zone of Avoidance, and we unpacked the wavelength physics that finally let us see the Great Attractor.
It's a lot to take in.
And only to find out that its massive dark matter core is just a way station on the road to the Shapley Supercluster.
It is a profound journey of scientific deduction, and, it is easy to feel small or insignificant when confronted with the sheer scale of the Shapley Supercluster. But understanding this grand, seemingly incomprehensible architecture offers a really vital shift in perspective.
How so?
Well, when you fully internalize that you belong to a structure so vast it requires tens of quadrillions of suns and an ocean of dark matter just to balance the gravitational scales, our local earthly concerns start to feel a bit more manageable. The daily stressors that consume us shrink down to their proper size when projected against the backdrop of the cosmic web. It doesn't strip our lives of meaning. It makes the fact that we exist at all, with the capacity to measure and comprehend this colossal gravitational dance, incredibly rare and special.
So what does this all mean? We're passengers on a journey we didn't sign up for, heading toward a destination we're only just beginning to map. But I want to leave you with a final thought to mull over, extending from everything we've covered in the sources. We've spent this deep dive detailing the pull, the velocity, and the megastructures waiting in the dark. But if we are hurtling sideways through space at 1.4 million miles per hour toward a gravitational nexus of tens of thousands of galaxies, what actually happens when we arrive?
That is the ultimate question.
Right. When our distant cosmic descendants eventually cross the threshold of the Great Attractor, or the Shapley Supercluster beyond it, does this ultimate destination result in a catastrophic, violent collision of superdense matter? Or is there so much space between the stars that we simply thread the needle, taking our place in a magnificent, endlessly complex orbital dance around the core? Next time you're sitting on the couch feeling perfectly still, just remember you are currently speeding toward the answer.